Chapter 6, Part 5, Properties of Stereoisomers and Racemic Mixtures. So if you have an enantiomeric pair of molecules, they will have an identical boiling point, melting point, and solubility. Because their 3D shape is identical except opposite, they're going to have all the same intermolecular forces. They'll even have the same pKa. They may have different chemical reactivity depending on whether you are interacting with something that's chiral, but often they're going to react in the same way. They will have equal but opposite optical rotation. We're going to discuss optical rotation shortly, so you can add a little more information to that later. And again, they have the same but opposite 3D shape. Diastereomers, because they have a fully different 3D shape, will have different boiling points, melting points, and solubilities, because again, they're going to experience different IMFs because they're different shapes. They will have different chemical reactivity potentially, especially with something that is chiral. And their optical rotation will not only be different, but it will have different magnitudes and even possibly directions of optical rotation. And their pKas are likely to be different as well. So what do we mean by optical rotation? When plain polarized light is shown through a sample of a chiral compound, the light will be rotated. When we take this measurement, we use something called a polarimeter. And a polarimeter is basically just a light bulb or a light source of some sort. This is a light bulb. And it shines light through a polarizer. So remember, light comes at us from all directions, but if you put it through something that polarizes it, you end up with light that's only going in one direction. So if you shine it through a polarizer, then it's only letting in light that is going up and down at that exact angle. And then it goes through a sample that is dissolved in typically water, if it's soluble in water, but it'll be dissolved in something that is achiral. So here's your sample. And then if this sample is chiral, it will rotate the light so that it no longer is on that plane. And then it's going to shine through a polarizer that is 90 degrees off from the original polarizer. Now, you may know this from like testing out sunglasses and things like that, but if you have two pairs of polarized sunglasses and you hold the lenses up together and kind of rotate them around a bit, eventually you'll find a point where the light is fully canceled out. And that's because one pair is rotating light in one direction and the other pair is rotating light or filtering light in the other. So if you have two polarizers that are filtering light in opposite directions and nothing happens rotation-wise in the sample, then no light should come out and the detector on the other side should see nothing. But if your sample is chiral and some sort of rotation happens, then the detector will see light and it will take the amount of light that it has and turn that into a number called the observed rotation or specific rotation. Sorry, that'll be the observed rotation and then it'll be normalized to the specific rotation. Now, if the rotation goes in the clockwise direction, we call that dextrorotary and we also assign a plus sign to it. If it's counterclockwise, we call that levorotary. You actually heard these words before when we talked about the difference between dextromethamphetamine and levomethamphetamine. The letters D and L do not correspond with R and S because this is a property of the molecule. And remember, molecules can have multiple chiral centers. So a D isomer could have 3 chiral centers that have the designation RSR, and then the enantiomer has the designation SRS, but rotates counterclockwise and is therefore levorotary. So D and L do not correspond with R and S. Enantiomers will have equal but opposite specific rotations. So, for example, these two molecules are enantiomers of each other. This first one is the R enantiomer of 2-methyl-1-butanol, and its specific rotation is in the positive direction, 5.76 degrees. Our S isomer rotates in the negative direction, but it's equal but opposite, negative 5.76 degrees. Now you'll see to kind of prove the point that R and S do not necessarily correlate with D and L. Notice that the R isomer had positive rotation here, but this R isomer has negative rotation. And these molecules are even alarmingly similar. The only difference is the hydroxyl group versus the chloro group. Okay, lastly, if you have a mixture that contains an equal molar concentration or a 50-50 mixture of two enantiomers, we call it a racemic mixture or racemate. And this happens sometimes as the outcome of specific chemistry. And you'll see this actually in chapter 7. We're going to learn about different substitution and elimination reactions. And the substitution reactions specifically have really interesting stereochemical outcomes. So if you have a racemic mixture, you'll observe no net rotation of plain polarized light because you have equal amounts of compounds that are rotating the light in opposite directions. The symbol for a racemate is DL, or you might see plus minus. A 50-50 mixture of R2-butanol and S2-butanol could be indicated as plus minus 2-butanol. And that would tell you that it is a racemic mixture.